Hello, and welcome to the Advanced Algebra video. I want to take a second to congratulate you guys on making it this far. We've come a long way from the beginner algebra rules, and today we're going to be expanding on some of the things we touched on in the intermediate algebra video. In the intermediate algebra video, we talked about how we could simplify expressions to make them easier to work with, because that would help us solve equations in the long run. In today's video, we're going to be doing much of the same thing. We're going to be working with something that pops up a lot in math, physics, engineering, pretty much everywhere that uses math, and that is polynomials. We're going to be learning how to expand them, how to factorize them, and how to work with them in fractions. And the goal of this video is to teach you guys how we can make polynomials look easier, and then also know when to use each of these three strategies. So first off, what is a polynomial? Polynomial is a type of expression that looks like this. We're going to have ax squared plus bx plus c equals d, where a, b, c, and d are numbers, and then the x is the variable that we're trying to solve for. Technically, polynomials can come in any shape or size that fits this right here. We are not limited exclusively to powers of 2. They can go all the way up to infinity, but for most of our purposes, we're going to be sticking with powers of 2. So the biggest power we're going to see is an x squared. Some of these techniques can be expanded into higher orders, 3, 4, 5, 6, 7, all the way out into infinity. But for most purposes, it's 2, and we're just going to stick to 2 for today's video. All right, so in the intermediate video, we touched upon how to factorize certain things. So for example, we had seen that we could have a 3x plus 6 look like 3x plus 2. Because what we had done is we recognized that there was a 3 inside of every term. So there's a 3 in front of the x, and then 6 is 3 times 2, so we could pull out the 3. And then I had mentioned that we could actually multiply into the brackets to get back our old expression, which is pretty intuitive. But what happens when we end up having something that looks a little bit more complicated? So for example, we could have an x plus 2 times an x plus 3. So now we're dealing with something a little bit different, because it's not just a single number multiplying a parentheses, it's actually a whole parentheses or bracket term multiplying an entire other bracket term. So when we first see something that looks like this, we could get a little overwhelmed, and it does look a little scary when we're first taking a look at it. But what's actually going on? Well, sometimes when I'm stuck on a math problem or a math concept, I try and break it down into something that's a little bit more ordinary, everyday type of situation. So what we've actually got is we've got two terms being introduced to another two terms. So let's say that we have a group of people going out to have some fun. Please ignore the poor drawing of the stick figures. I am trying my best. So we've got two people that already know each other going out, and they bump into another group of two people that are going out. Now, what are we going to do? We've got a group of people that know each other in the black group. We've got a group of people that know each other in the blue group, but the black group doesn't know the blue group. So what do we do when we're in a social situation and we've come up with a new group of people? Well, first we're going to say hi, introduce ourselves. So this person right here is going to introduce themselves to the first blue person, and then they're going to introduce themselves to the second person. Now, since the two figures in the first bracket already know each other, it'd be really silly for them to introduce themselves to each other because they already know each other. So after this person introduces themselves to the new two people, the second person does it as well. And so once everyone in the first bracket has introduced themselves to everyone in the second bracket, we can go, aha, we've all introduced ourselves, we all know each other, and now we can start to group together and talk to each other without there being so much awkwardness because we don't know each other's names. So the same thing is actually going on in the math case up above. So the question becomes, what is the mathematical equivalent of introducing ourselves the way the people did? Well, the way we actually are going to do that is the same way that we handled the 3 at the very top, where 3 was saying hello to x by multiplying, and 3 was saying hello to 2 by multiplying. So we're going to have that exact same thing happen. So we're going to have x plus 2 times x plus 3. Now I'm going to color code the interactions for a reason that's going to be apparent later on. So the first thing we're going to do is x is going to say hello to x. All right. Next, x is going to say hello to 3. Now, the first term of the left bracket has now introduced themselves to absolutely everyone in the second group. So we're going to have an x and an x. Well, x times x is just x squared. Next, we're going to have the introduction of x and 3. So that's going to be 3x. Now, for the second term of the first bracket, he needs to introduce himself too. So what he's going to do first is he's going to introduce himself to the x. So 2 says hello to x, which means that we're going to have a plus 2x. And then finally, 2 is going to introduce himself to the 3. So we're going to have 2 times 3, which is going to be 6. So just like that, we now have a fully expanded out polynomial. We've got 2 bracket terms, they introduced each other, and then we can actually combine and we're going to end up having a slightly simpler expression that looks like x squared plus 5x plus 6. Now the reason I color coded it is so that we could see that there's actually a pattern that's being developed. So there's only going to be one multiplication that's going to result in an x squared, and that's the blue one, because that's the one case where the x introduces himself to the x. There's the red term, which is what happens when the x's talk to the non-x's. So the x talks to the 3, that gives me that red 3x. The 2 talks to the x, that gives me that red 2x, for a total of 5 red x. All right, and then the green term is what happens when the 2 non-x's talk to each other. So we notice that there's only one blue term, because there's only once that the x's introduce each other. There's only one green term, because that's when the 2 non-x's introduce to each other, but there's 2 red terms, and that comes from the x's touching the non-x's and introducing each other. So what we're going to have to walk away with here as an understanding of how this works is that the red is an addition and the green is a multiplication. All right, so we get to red by adding the 2 numbers, so 2 plus 3 gives me a total of 5x, and we get the green by multiplying the 2 and the 3, which gives me a 6. So we're going to want to hold on to that idea. That is a key idea for later when we talk about factoring. So just keep that system in mind. Keep that little pattern in the back of your heads. So in the case up above, we had managed to expand out 2 polynomials that were touching each other by introducing them to one another. But what happens if we change it up a little bit? So for example, before we had x plus 2 times x plus 3, but let's throw in a minus this time. What happens if we've got a mix mash of pluses and minuses. Well, we're going to have x and x, which gives us our x squared. We're going to have x saying hello to minus 3. Now, these are all multiplications, so minus 3 times x is going to give us a minus 3x. Next, because the first x term has introduced himself to everyone, now it's the second term's turn to introduce himself to everyone. So we're going to have 2 say hello to x. And now these are two positive numbers, so we're going to have a plus 2x. And then finally, we're going to have the 2 introduce himself to the minus 3. Now this is a positive 2 times a minus 3, so that's going to be a minus 6. All right, now in the case where everything was nice and positive, everything just added up nicely. Here the same thing applies, it's just that that little negative sign is going to mean that it's going to be a subtraction in the red terms. And then we have to be careful when we're multiplying the two non-x terms, because the fact that there's a minus is going to change the sign. But at the end of the day, we are still going to end up getting, oops, that's not right, my bad. We are going to get a term that's still easy to work with. We're still going to have an addition in red and a multiplication in green. We just have to be a little bit careful when there's a mixed matched sign, because we're going to have negative terms popping up, and those little negative signs can really screw you over if you're not careful. Now I'm going to give another example of how this could get a little bit trickier than it already is. But again, I want you to keep in mind, we're still doing an addition of the two non-x terms for the red and a multiplication of the two non-x terms for the green. Now sometimes we'll have something that looks like 2x plus 1 times 3x plus 4. So this is going to be about as tricky as the powers of 2x are going to get, but the actual work itself is going to be the same. So again, we've got two groups of people that need to introduce themselves to each other. 2x says hello to 3x, but now it's going to be a little bit complicated because it's going to be 2x times 3x. Then the 2x says hello to the 4. So we're going to have 2x times 4. Next, the 2x has said hello to everyone. Now it's number 1's turn to say hello to everyone. So we're going to have 1 times 3x. And then finally, the number 1 is going to say hello to the only non-x term on the other side, which is the 4. Now, these were all positive, so these are all going to be additions. But we noticed that this case is a little bit trickier because of the numbers in front of the x term. So I wrote it out like this so I could show you what's actually going on, because I find that sometimes students get a little stuck when we've got numbers in front of the x's, and it can be a little hard to tell sometimes, like what is 2x times 3x? Well, the trick is actually way back in the beginner algebra video, where we talked about how if you've got all multiplication and division within a term, the order doesn't matter, because 2 times 3 is 3 times 2, they're both 6. So what's going to happen is I'm going to choose an order that makes it easier to see what's going on. So we're going to have 2 times 3 first, and then x times x. Then we're going to do 2x times 4. So we're going to have 2 times 4 times x. And then we're going to have, well, 1 times 3x is already as easy as it's going to get, because it's literally just 3x multiplying by 1. Anything multiplied by 1 stays the same. So it's going to be 3x. And then finally, we're going to have the green term, which is 1 times 4, which is just 4. So what are we going to get? Well, we're going to get 2 times 3, which is 6. We're going to get x times x, which is just x squared. Because remember, those little exponents just tell you how many times we're multiplying something by. And then for the red terms, we're going to have 2 times 4, which is 8x, 3x, which is just 3x, plus the 4. And then we can start to combine the terms, and then we're going to get 6x squared plus 8x plus 3x is 11x, plus the green term, which is 4. So even though the second polynomial here looked more complicated and involved more work than the top one, the structure is still the same. We still have a single blue term, which is the 2x terms multiplying each other. Sometimes 2x times 3x looks a little harder than just x times x, but it's still a multiplication at the end of the day. So you multiply the two numbers in front of the x together, so in this case 2 times 3 to give us 6, and then x times x is still just 6, is just x squared. Notice that the red terms are still 2 because there's 2 non-x terms, and it's still an addition. There's a little multiplication to do first because you've got a number in front of the x term, but once you take care of that, you're still adding together 2 red terms. It's still an addition. There's just a little multiplication because of the 2 in front of the x and the 3 in front of the x. But at the end of the day, you're still doing an addition. And then finally, the green term, there's only 1 because there's only 2 non-x terms, and so when they introduce themselves to each other, it's literally just the 1 term. If we had a negative sign in the second case, where we've got 2's and 3's in front, it would be the exact same as the first polynomial up top. I'll have some extra fun bonus problems with a mix of positive and negatives with numbers in front of the x's, like this bottom case here, but for now, I'm going to move on. All right, now that we've got a pretty good handle on how to expand, we can ask the question, why? Why are we bothering to learn how to do this? Why is it useful? Well, part of the answer is math is fun, so sometimes it's fun to do it just for the fun of doing it. But other times, there's an actual useful reason for why we do the things we do. So let's say we had an expression that looked a little bit different from what we've seen before. So let's say we've got an x minus 1, and then it's being multiplied by an x minus 2. And instead of just being an expression that we expand out, we make it actually equal something. So before we were looking at expressions, and now we're looking at an actual problem. All right, so let's say that this was an equation that looked like minus 3x plus 6. All right, now at first glance, yeah, this looks a little gross, doesn't it? We've got 2 bracket terms with x's multiplying each other. We've got a spare x on the other side and another non-x term on the right just doing its own thing. And we want to know, okay, well, what is x equal to? It's hard. It's hard to solve as is. So what we can do is we can expand out the polynomials that are multiplying each other on the left-hand side, because expansion can be really useful when we want to combine terms together. So I'll show you what I mean. We're going to go through the quick little exercise, but a little bit faster this time because I've shown you guys a couple of times now how to do it. So we've got x and x, well that's going to be x squared, x and minus 2, that's going to be minus 2x, minus 1 now has to say hello to everyone, so we're going to have a minus x, and then finally minus 1 says hello to minus 2, negative number times a negative number equals a positive number. And that's still going to equal minus 3x plus 6, because we haven't done anything to the right-hand side. And all we've done is rewritten the left-hand side in a way that's going to make it easier to solve this equation. So let's combine the like terms on the left-hand side. We're going to have x squared minus 2x minus x, that's a total of minus 3x, plus 2 equals minus 3x plus 6. And look at that. All of a sudden, we can start to combine some of these terms. So one of the things that jumps out to me is the fact there's a minus 3x on the left-hand side and a minus 3x on the right-hand side. So that means that when the moment that we try to get rid of a minus 3x on the left, we automatically get rid of it on the right-hand side. So you can try it on your own, add 3x to both sides and see what happens. Or you can trust me for now, and we'll see that this actually cancels out. So the 3x cancels out the minus 3x, and now we've got x squared plus 2 is equal to 6. And now we can ask ourselves, what's next? Well, remember, when we're doing algebra, we want all the x terms on one side, everything else to the other. So we're going to end up having something that looks like x squared equals 4. Now this term at the very bottom is quite a bit easier to solve than the original term up top, because I could not tell you just by looking at the term up top what x is equal to. Whereas if you're good at your multiplications tables, we'll be able to quickly see that there's actually two answers that satisfy x squared equals 4, and that is x equals 2 and x is equal to minus 2. Because if you do 2 times 2, you get 4, so that works out. And if you do minus 2 times minus 2, that equals 4 as well, and that works out. So in this case, expansion let us take a really gross, ugly equation, and it helped us come up with a really easy way to solve an equation. So why expand? Because sometimes you've got a mix of terms. Sometimes you've got a bunch of x terms on the left-hand side and some x terms on the right-hand side. And when you expand it out, you might be able to cancel stuff out, or you could group things together in a way that'll make it easier for you to solve. So if you ever find yourself in a situation where you've got a mix of terms on the left and the right, you can try expanding so that you can collect the terms together. And then from there, you might be able to get a really easy solution. Now, let's take a look at one more very quick example of when expansion is useful. All right, so this example is going to be a little bit trickier. We're going to have x plus 3 times x plus 2, and that's going to equal, well, let's just say 5x plus 2. So again, we take a look at this expression on the left-hand side. We know that we can change the way the left-hand side looks. And then looking at the entire equation, I can't tell what the heck x is going to equal. So because I recognize that I've got a mix of terms on the left and the right, my brain goes, aha, let's try expanding. So I'm going to go a little bit faster this time and show you a little quick trick. So there's two x's by themselves, and now it's going to be x squared. I know the 3 and the 2 add up together to 5, so it's going to be 5x's total. And then we're going to have 3 times 2, which is going to give me a 6. Oh, I forgot to make this a minus 5. My bad. There we go. And that's going to equal minus 5x plus 2. All right. So what's going on here? Well, we can do a little bit of algebra to try and bring all the x's to one side, everything else to the other. But that's actually not going to help us in this case to solve this equation. What we're instead going to do is we're going to rewrite this equation so that it looks like a polynomial. Ax squared plus bx plus c equals d. But in a little bit of foreshadowing for what we're going to do next, I'm actually going to make it look like ax squared plus bx plus c equals 0. All right, so let's combine all these terms together. Well, there's only one x squared on the left-hand side, and I usually just choose to put the x's wherever the biggest power of x is. In this case, it's on the left. So I'm going to move the x term on the right over to the other side. This is a minus 5x, it's a subtraction. So from the beginner algebra video, we get rid of subtractions with additions, and we're going to get x squared plus 5x plus 5x plus 6 is going to equal to 2. We're going to combine the terms. X squared plus 10x plus 6 equals 2. And now we're going to move the 2 over to the other side. And we're going to have x squared plus 10x plus 4 is equal to 0. Now, we still can't solve at this step right here, but this looks a lot nicer than this top term up here. So even though we still can't quite solve it, we've actually managed to make it look nicer, which is a good first step. So this is going to lead us to our second problem, which is how are we going to solve this bottom expression, this bottom equation. And the way we're going to do it is actually a little bit counterintuitive. What we're going to do is we're going to factorize the bottom equation so that it looks like x plus some number times x plus some other number, which I'm going to use a different symbol for, equals 0. Because if we can make this bottom equation look like this, we'll have a multiplication of two numbers, because remember, even though these have x's, the x is still just a number at the end of the day. So we've got some number times, some number 1 times some number 2 equals 0. And when we're multiplying, the only way that we'll ever get a 0 through a multiplication is if we're multiplying by the number 0. So what does that mean? That means that either this term is equal to 0 or this term is going to be equal to 0. So the idea is if we can make this bottom equation look like a multiplication of two terms equaling to 0, we know that each one of the terms has to be a 0, because the only way for multiplication to be a 0 is if either the blue term is 0 or if the red term is 0. So in this case, expansion didn't let us solve the equation the way the last one did, but it helped us put the equation into a position where we can use this little 0 times 0 trick to solve the problem. And that right there is factoring, and that is our very next topic. All right, so I have found that factoring is something that can cause students a little bit of trouble, but the funny thing is it's actually one of my favorite things to do. So in the last example, we saw how we could expand two terms that are multiplying together to create a big polynomial, and how expanding could help us solve. Now we're going to do the opposite. So we're going to factorize in order to solve. So let's start off with a simple little expression to show us what's going on. Let's say we have x squared plus 6x plus 9 is equal to 0. Now, whenever we're factoring, we always want the right-hand side to equal 0, because that's what's going to let us actually do the little 0 times 0 trick to solve. So I'm just going to get rid of the 0 for now, but remember that it always has to be equal to 0. And what we want to do is we want to make this expression look like two parentheses terms that are multiplying each other. Because remember from the last example, if the left, in order to have a multiplication equal to 0, one of the multiplication terms has to be 0. That's the only way to get a 0 out of a multiplication. We look at the x squared term first, because that's going to be our little guide. That's the easiest way to figure out what's going on. And if we remember from the expansion video, we've got the x and the x multiplying each other, which gives us that x squared term, right? Oh, except I had done it in blue before, so let me be consistent. We're going to do x times x is going to give us that x squared term. And then remember that what we're really looking at is two terms adding together. And I know it's two terms adding together because it's all positive over here. So what's going to end up happening is we're going to have a non-x term. We're going to have a non-x term multiplying an x, and then we're going to have an x multiply a non-x. So remember that the red lines being the non-x touching the x. And then we're going to have one final term, which is where the non-x says hello to the non-x, right? So what that's going to do is it's going to give us a list. So we remember from the expansion part of this video that the red arrows have to add. So the red arrows make up terms, so we know that we have to add to 6 and that we have to multiply to 9. And there's a couple different ways to do it, but the easiest way is to look at the multiplication. And why is that? Because there's actually quite a few ways to add up the number 6. So you could have a 1 and a 5, a 2 and a 4, a 3 and a 3. Whereas if you want to multiply by 9, you really only have the one choice. It's either, well, two choices, I guess. It's either 1 and 9 or 3 and 3. So in this case, we're going to use the multiplication to give us a list of options. So we're going to have the number 1 x term, the number 2 x term, 1 and 9, 3 and 3. Now, I know that the green is giving me a list of options to choose from. Which one do I choose? Well, the x is going to let, sorry, the red term is going to let you know. So if I added the 1 and the 9, then that means that we'll have a 10. And if we do the 3 and 3, we'll have a 6. So I can see here 3 and 3 multiply to the green 9, which is what I want. They add up to the red 6, which is what I want. So that way I know that the non-x term and the x terms multiplied together and then added will give me the right number, which is 6. And then the non-x times the non-x, the 3 and the 3, will give me the multiplication that I want. So that tells me that we have x squared plus 6x plus 9 equals x plus 3, because that's our first term, and then x plus 3, because that's our second term. And remembering that because we're factoring, we have everything equal to 0 right over here. So now we're almost done. We might be asking ourselves, okay, well, what's going on here? Well, what's going on is that this term, the first term, and the second term have to be 0. Now, in this case, they're both the same, so there's only one answer. So which is basically the answer will be this turns to 0 when x plus 3 is equal to 0, which means that x is equal to minus 3. So we can see that factoring puts this into a position where all we have to do is solve one little expression, which is pretty simple. And if we hadn't have factorized, we'd be dealing with x squared plus 6x plus 9 equals 0. Now, if you have a choice between solving x plus 3 equals 0 or x squared plus 6x plus 9 equals 0, I know which one I'm choosing. I'm choosing x plus 3 equals 0 all day long because it's a lot easier. So this advanced algebra video is really about showing you guys a bunch of different techniques to make expressions easier to look at, which in turn makes it easier to solve. So if you've got mixed terms like in the previous example, expansion is a good way to start. If you've already got something that looks like ax squared plus bx plus c equals 0, or if you can make your expression look like ax squared plus bx plus c equals 0, factoring. Factoring is a really great place to start because we're going to have an x plus a number term equal to 0 as opposed to an x squared term, an x term, and a non-x term mixed all together. All right, so I'm going to give you guys another example of factoring polynomials to show you how it could get a little bit trickier. And then from there, we'll start getting into some fancy factoring after that. In the previous example, we looked at factorizing a polynomial that had all positive terms. But in real life, we don't always have that luxury. Sometimes we'll have polynomials that look like x squared plus x minus 6 is equal to 0. And now this one's going to be a little bit trickier because we're looking at a positive term and a negative term. So we've got a positive x and a minus 6. So because we've got a mix of positive and negatives, I know that the roots are going to have a mix of positive and negative. All right. Now, remember that the x term is the addition term. The non-x term is the multiplication term. So it looks like we need our x terms to add to 1, and we need them to multiply to minus 6. So remember that we use the multiplication to give ourselves a list of numbers to choose from, and then we use the addition to actually pick between the list of choices that the multiplication gives us. So for the multiplication, we've got a minus 6. Because it's a negative, it's going to be a little bit trickier. So we're going to have a minus 1 times 6 gives us minus 6. We're going to have a positive 1 times minus 6 gives us minus 6. And then we're going to have 2 and negative 3. And then we're going to have negative 2 and 3. So we can see here that the addition of a minus term mixed with a positive term has given us quite a few different options because we have that mix of negative and positive. One of the numbers has to be negative, the other number has to be positive if we want to have a negative multiplication. Now, if we started to add up these multiplication numbers, minus 1 plus 6, well, that's positive 5. And here we have a 1x. 1 positive x. So I can already immediately rule out the first couple ones because obviously 1 and 6 are not going to get us anywhere close to that. 2 plus minus 3, that gives us minus 1. Negative 2 plus 3 gives us 1. So I see that I needed an addition of 1. So that looks like this bottom term down here is the one we actually want. So what is that going to look like? That means that our polynomial is going to look like x minus 2, x plus 3. And remembering that when we're factorizing, it's very important that everything be equal to 0. Because the reason we can solve in the first place is because we're using that logic of whatever number is in the first term, whatever number is in the third term, has to be 0, because the only way to get a multiplication to give you 0 is if one of those numbers is 0. And in this case, the two roots, which are the terms inside the brackets, we usually call them roots, are different. So we're going to have two different answers, which is really cool. We get two different answers to an equation and they both work. So we're going to have x minus 2 equals 0, x plus 3 equals 0. So from there, we can really quickly see, okay, well, x has to equal 2, and x has to equal minus 3. So something that I want to give a quick little shout out to is that sometimes when you're in an exam and you're stressed or you're rushed, running out of time, sometimes people will find these roots minus 2 and 3 and then immediately write down, oh, these are what the x values are. No. These are the roots inside of the parentheses, which give you an easy equation to solve. But when you actually solve for x, you'll find that you'll get the opposite sign. But I find that it's best not to memorize things, but instead to understand where they come from so that your brain doesn't brain fart on you during an exam. Now, comparing these two equations, x minus 2 equals 0 and x plus 3 equals 0 with the original polynomial, which is x squared plus x minus 6 equals 0. Again, very different looking equations, and I would very much rather choose x minus 2 equals 0 and x plus 3 equals 0 over this ugly blue term down here. So once again, when we factorize, we want to have everything set to ax squared plus bx plus c equals 0, where a, b, and c are whole numbers. And then we can factorize because that gives us a set of equations that are the same as the blue equation, but they look way easier and are in fact way easier to work with. So remember, algebra can be used to make things look easy, and if you can make things look easy, please do so, because easy is better than harder. Now we're going to quickly move on to another example. All right, so far we've been looking at some fairly straightforward factorizing, and now we're going to kick things up a notch where the x term's not going to look, the x squared term's not going to look the same way it has before. So we're going to have 2x squared plus 5x plus 2 equals 0. Again, very important that we have this set up in a situation where the other hand is 0. If it's not 0, you got to move everything over to one side, keep it 0, otherwise our whole logic falls apart. This is going to get a little bit more complicated because of one term, and that's this guy right here. So he's going to make things a little bit more complicated, but even then, this is actually still not too bad. So I'll show you what I mean. We're still going to want to make this polynomial look like a multiplication of two bracket terms, but we need something a little bit different. Before it was always x and x because we had an x squared term, but now we've got a 2 in front. Now here it's actually not too bad because the number 2 is prime. So what that means is the only way we can get to number 2 with whole numbers with the multiplication is if one of them is a 1 and the other one is a 2. You know, we've got 1 times 2 equals 2. Technically, we could do -1 times -2 equals positive 2 as well. But since all of the other terms are positive, I know that this isn't going to fly. So I know that the -1 times -2 is not going to work. If there was a mix of negative and positive terms, then we'd have to include it. But right now, we don't. Right now, we got lucky. We've got a prime number here. So we're going to have 1 times 2 equals 2 is the only way to have two whole numbers give you the number 2 through a multiplication. Now we're going to have the same logic as before. All right, we're still going to have a non-x term multiply an x term and vice versa. And then we're still going to have the non-x term multiply the non-x term. All right. And then of course we're going to have our x and x say hello to each other to give us that 2x squared like we wanted. So here we're going to see the power of choosing green, of having the multiplication. So we know that we have to multiply to 2, right? And we know that we're going to have to add to what? Well, you remember the addition is the x term, not the x squared, not the non-x, but the x term. So we know that we have to add up to 5. So we need to multiply to 2. Well, that's fairly straightforward. There's only a couple things we could do. We could do 1 and 2, and we could do -1, -2. Now, this is going to get a little bit trickier though, because of this 2x term right there, this little guy. That 2x is going to multiply, or is going to be multiplied by this non-x term in here, which means that one of these two numbers has to be multiplied by the number 2, because it's not x times the number, it's 2 times x times the number. So actually I'm going to erase this real quick right here so that I could have 1 and 2, 1 and 2, -1, -2, -1, -2. Now, why am I repeating? I'm repeating because we've got that 2 term. We've got this 2x in there, which means that we're going to have to take turns. That means that maybe the 1 gets multiplied by the 2 because of the 2x in front, or maybe the 2 gets multiplied by 2. All right, so let's do it really quickly. We're going to have this 2x multiply this non-x term. So that's going to be 2 times 1, which is 2, plus the other non-x term. And we're going to get ourselves a 4, which comes from 2 times 1 plus 2. 2 times 1 plus 2. That's 4, that's close, but remember, it's that x term that we want, the addition to 5. So let's take a look at the second one. We're going to leave the number 1 alone this time, and this time we're going to do 2 times 2. So what's that going to equal? We're going to have 1 plus 2 times 2, which is 1 plus 4, which is 5. And look at that. We've got an addition to 5, and then we've got a green multiplication, 1 times 2 to the 2. So this set of numbers right here actually satisfies our conditions. So we're going to have 2x squared plus 5x plus 2 is going to look like 2x. Notice both green numbers are positive, so I know this is going to be a positive. X positive equals 0. Now in the previous examples, because it was just x times x and there wasn't this weird term in front of the x squared term, it didn't matter where we put the roots. This time it does, all right? Because if we notice with the purple, it is the number 2 that gets multiplied by 2, all right? So if you remember from the expansion video, if I were to put the 2 in here, well, these two terms already know each other. So they're not going to say hello. The 2x is not going to multiply the number 2 because it's already inside the bracket. So the only non-x term that the 2x is going to multiply is actually over there. So because this is the only non-x term that the 2x is going to multiply, and we know that the 2 has to be multiplied by 2, that tells me that the 2 has to be right here. So before, we could put them in willy-nilly because it didn't matter, but because of this term in front of the x, now it really does matter. All right? And then because we already have the 2 terms selected, well, that means that the 1 term is just right over there. And so once again, we've got ourselves 2 equations. We've got 2x plus 1 equals 0. Because remember, we've got a multiplication of some number times some other number equals 0. So either the first number is 0 or the second number is 0. Now, for the bottom one, it's really easy to see. You just move the 2 over, and we got x equals minus 2 as one of our answers. And then for the number 1, well, remember when we're doing algebra, we want to move all of the x's to one side, everything else to the other. So in this case, I could move the 2x over to the other side, but then I'll have negatives kicking around, and I don't like having negative x's kicking around. So instead, I'm going to move the 1 over. So we're going to have 2x equals minus 1. And then from there, we're going to have x is being multiplied by 2. We get rid of multiplications with division. X equals minus 1/2. And just like that, we've got ourselves 2 answers to the equation. And even though equation number 1, 2x plus 1, looked a little bit trickier than the other examples, I would still much rather take 2x plus 1 equals 0 or x plus 2 equals 0 instead of 2x squared plus 5x plus 2 equals 0. So the point of this example is to show you guys how to solve equations when the x squared term has a number in front of it other than the number 1, like we saw in every other example so far. So remember, very clear, ax squared plus bx plus c has to equal 0. In the case that a is equal to 1, it's pretty straightforward, but when a is not equal to 1, we have to remember, okay, we need to figure out how 2 numbers will multiply to give us the letter a. And then when we choose, again, we use the non-x term to give ourselves a list of possibilities, and then we have to figure out which one of these green multiplication terms is going to end up getting multiplied by the numbers that give you the letter A in front of the x squared. All right, this is going to be our final example on factoring polynomials. And since it's the final example, we're really going to be kicking things up a notch. We're going to be making the factoring itself quite a bit trickier. And on top of that, we're going to change a little bit of why we're factoring. So far, we have been factoring ax squared plus bx plus c equals 0, so that we could get x plus some number, x plus some other number equal to 0, and then that lets us solve immediately. But remember that the advanced algebra video is all about showing us how to make things easier to look, easier to work with. It's not always about solving. Sometimes the hard part's actually just making the equation look easy. So we're going to change things up a notch, and instead of factoring in order to make everything look easy to solve through solving directly, I'm going to show you guys a different motivation, a different reason why we should factorize. All right? Now let's assume that we've got something that looks like 6x squared plus x minus 1 divided by 2x plus 1 equals 0. Now, looking at this, we can go, what is going on? It's easy to get a little overwhelmed sometimes. All right, so we've got a big polynomial of order 2 because there's an x squared. There's a polynomial of order 1 because there's just an x term down below. It's equal to 0. What's going on? What can we do here? Well, we're going to try factoring. And the reason we're going to try factoring is whenever we see a big polynomial being divided by a smaller polynomial, we can try to factorize the top polynomial to see if we can cancel out the ugly term underneath. So that's what we're going to do. We're going to focus on factorizing the top term to see if maybe we can cancel out that bottom term. All right? So here's what's going to happen. We're going to look at 6x squared plus x minus 1 is equal to some set of brackets. All right? Now, the number 6 is going to be a little bit trickier to work with. All right? Because remember from the previous example, when we have a term in front of the x squared that's anything other than a 1, it means that it's going to multiply the non-x terms. So we need to figure out how to break this 6. All right, so we want to break down the 6 into a couple of numbers, because remember that the 6 is going to multiply the non-x terms. So we're going to have 1 and a 6. We could have 2 and a 3. And that's about it for now. That's all we're going to explore. Because remember, we want to multiply by nice clean numbers. So in the previous example, the number in front of the x squared was a prime number, which means that they gave us just the one choice. 6 is not a prime number, so we've got multiple choices to choose from. But there's actually a little trick to help us choose between the 1, 6 and the 2, 3. Now remember that our motivation right now is we want to factorize the top to see if we can cancel out a bottom term. And I see that the bottom term has a 2 in front of it. There's a 2x. So because I'm trying to explore whether or not I can cancel out the bottom term, it makes sense to pick the terms that look like the bottom term. So for me, that's going to be the 2 and the 3, because we're going to have something that looks like 2x and 3x. And then that's going to tell me, oh, okay, yeah, we've got a 2 and a 3, we've got a 2 and a 3. The bottom term has a 2x. Well, this is already starting to look pretty close. So I'm going to choose the 2 and the 3. It could be the 1 and the 6, but we're going to choose the 2 and the 3 because if it turns out it's 2 and 3, we're good to go already. Now, remember that we have a red term, which was the addition term, which comes from the non-x terms interacting with the x terms. So we've got an addition that has to be 1, because this is 1x. And then we need to multiply to -1. Now, this problem is going to be a little bit trickier than the ones we worked with, not just because of the purple, but also because the fact that I've got a positive x and a -1, that tells me that we are going to have a mix of positive and negative terms. So if we want to multiply to -1, it's relatively straightforward. You've got 1 and -1, 1 minus 1, and that's basically it. So we actually got a little bit lucky. Even though the x squared term looks really gross, the non-x term came to save our butts, basically. And we're actually going to need a few more right over here. So from the previous example, we saw that the purple terms end up multiplying the non-x terms. So the purple terms are actually going to affect what these terms add up to. So let's go through it. We've got a 2 and a 3. So maybe we multiply the positive 1 by 2. Maybe we multiply the -1 by 3. Maybe we multiply the positive 1 by 3. And maybe we multiply the -1 by 2. Now, I included the 1 minus 1, 1 minus 1 down below, just in case we had to use the separate numbers of purple, of 1 and 6. But we're just going to try out 2 and 3 to start with. I just wanted to write them out below so that you guys could see how having a non-x term and a mix of positive and negative terms can really screw us up over here. Oh, and I don't know why I put -3 there, my bad. Positive 3. Because the 2 and the 3 are positive, because 2 times 3 has to give us 6. We could have included -2 minus 3 as well, because -2 times -3 also gives us a positive 6. But again, I chose the 2 and the 3 because I'm checking to see if I can actually cancel out this bottom term. So notice that we've got a lot of options, and what I'm using to choose between them is sometimes just a little intuition, sometimes just saying, well, I want these things to cancel out, so let's just pick the term that's going to make it look like it's going to cancel out to help us out. All right, so we've got a list of green, which is the multiplications of -1. We don't know whether the 2 or the 3 is going to be multiplying the positive or the negative, so we've got to check out both cases. All right, so if we check out the first case, we're going to have 2 times 1, which is 2. We're going to have -1 times 3, which is 3. So we're going to have 2 minus 3, and that gives us -1. And look at that. We wanted to add to +1, -1, not quite there yet. If we do 3 times 1, which is 3, and then we add it to -1 times 2, which is -2, we're going to have 3 minus 2, which is 1. And look at that. We've just solved for what the roots actually are. We've got the multiplication by purple because of the 6x squared term. And we've got the multiplication by -1 in green. And together they added up to 1. So remember, the green multiplication gives you a list. The purple term in front of the x squared, it means that both of the numbers are going to get multiplied. So we've got to check to see which ones, and then we check by making sure that they add up to that red added x term. So great. It looks like we're going to have 6x squared plus x minus 1 actually looks like 2x, 3x. All right. Now, again, we've got to be very careful because remember, it depends which purple number is multiplying which green number. That's why this top example and the bottom one are different. So in this case, it looks like the 3 is multiplying the 1. So that means that 3 is going to multiply this number here, and that's going to be the 1. And the 3 is multiplying the positive 1, so this one is positive. All right, and now we see that the 2x is going to be multiplying the minus 1. So this is going to be a minus 1 that it's multiplying. So that's great. We've got ourselves two solutions, or we've got ourselves, not two solutions, we've got ourselves two factors. So we can make 6x squared plus x minus 1 look like 2x plus 1 times 3x minus 1. Now, sometimes when we're in a rush, we might be so used to factorizing that we'll jump immediately to, oh, this equals 0. Our answer is, but that's not what's going on here. So sometimes when you feel like you're almost done, it's a good to force a habit to remember what we're actually solving in the first place. And what we're solving is not 6x squared plus x minus 1. We're solving this whole division. So what does that mean? That means that when we have 6x squared plus x minus 1 divided by 2x plus 1, what that actually looks like is 2x plus 1, 3x minus 1, divided by 2x plus 1. All right, so look at here. We've got 2x plus 1 on top, 2x plus 1 at the bottom. Sometimes it can be a little hard to see what's going on when we've got such complicated expressions. So sometimes I'll just break it back down into regular numbers. Because remember, at the end of the day, these x's are numbers. So we've got, let's pretend that this bracket here is the number 2. We've got 2 times this divided by 2. We're multiplying and then dividing by the same number. So if you remember the basic algebra video, if we're multiplying and then dividing by the same thing, and it's all multiplication and division, the order doesn't matter. So I'm going to choose to do 2x plus 1 divided by 2x plus 1 times 3x minus 1. And the reason I wrote it out like this is because I wanted to show you guys that this 2x plus 1 actually cancels out, because anything divided by itself is just 1, and 1 times anything is just that same thing. So then we're going to have that the whole thing is actually 3x minus 1. So we have the original really ugly polynomial division, and we ended up getting something very simple, which is 3x minus 1. All right, and then if we tried to solve for 3x minus 1 equals 0, because remember that this division at the end of the day was always equal to 0, this becomes pretty easy to solve, and we get x is equal to 1 over 3. Now, if we had simply solved the factoring, forgetting about this bottom term right here, we would have generated two solutions. We would have generated the 3x minus 1, and we would have generated the 2x plus 1. All right, so it looks like we've got more answers than we actually do. Why is that? And that's because if we had factorized and solved for 2x plus 1, equals 0, then 2x plus 1 equals 0 would have given us an answer for x that would have led to a division by 0, which is something we don't want to do in the first place. We don't want to divide by zeros. So if you forget what we're actually solving and you get stuck in that factorizing, oh yeah, I'm factorizing, oh yeah, I found the factors, oh yeah, I found the two equations, oh yeah, let's solve, you can fall into a trap where you get an answer that's not allowed, because we do not want to divide by 0. So whenever you feel like you're about to finish and you're going to circle off that answer, double check the question they're actually asking you. Because when you're working with longer algebra, more advanced algebra, it's easy to get lost on the journey. So just double check and remember, oh yeah, what we're actually trying to solve is a division, not just factorizing. And then we'll get ourselves the right answer. Because if you're not careful, you might end up getting an answer that's not actually allowed. So the reason that this example was a little bit trickier, and the reason I designed this for you guys, is because I wanted to show you multiple things going on at the same time. I wanted to show you a situation where the term in front of the x squared is not a prime number, so we've got multiple lists of purple to choose from. I chose 2 and 3 because I wanted it to cancel out the bottom term. So that's why I figured, okay, well, I want it to look like 2x plus 1 at the end of the day. So the purple I chose based on what I wanted to cancel out at the bottom. I wanted to show you guys how that combines with this mix of positive 1x minus 1, because that mix of positive and non-positive means that you have to generate the list a couple times, because you've got a negative and a positive mixing together. And then finally, to show how those actually mix together with the purple. So we had to do it twice because we don't know if the first purple number is going to be positive or if the other purple number is going to be positive. At the end of the day, we add a little bit of complexity, but we're still making sure that the greens multiply to that non-x term, and that the combination of purple and green gives us red, which is that 1x term in this case. And the other reason I wanted to show you guys this example is because sometimes we get so used to thinking about factoring as a way of solving, as in just setting this whole equation equal to 0 and walking away. Sometimes factoring isn't a way to solve. It's a way to make it look easier so that we can solve afterwards. So if you've got a polynomial being divided by another polynomial, a good force of habit, a good thing to check is let's factorize and see if some of these terms cancel out. Because if I can make the top and the bottom look like multiplications and divisions, and they've got a term in common, I can cancel it out and save myself a whole bunch of work. So if this last one was a little bit much for you, don't worry. I did that on purpose. I did that so that you guys can see, oh, okay, there's a lot going on, the logic is the same, and it's not always about solving. With advanced algebra, sometimes it's about making an expression look easier to work with, because that lets us solve indirectly. So even though factoring didn't directly solve, it sure made solving a whole lot easier. Now, if you're writing a test, you're running out of time, so it takes a while to factorize something that looks like 6x squared plus 1x minus 1. And you might be asking, is there an easier way? And there actually is. So in the next example, we'll do the exact same equation, and we'll see how there's a much faster way to solve in case you're in an exam, or you're rushed for time, or you just really having a hell of a brain fart. There's a way around it. All right, so in the last example, we were trying to factorize something that ended up being a little bit of a monster, and that was 6x squared plus x minus 1 equals 0. We were trying to factorize it in order to simplify an expression, but sometimes we just want to factorize because maybe there isn't a term down below and we just need to factorize to solve. So what do? Well, the first thing we do when we're factorizing, as always, is we want it to look like ax squared plus bx plus c equals 0. So in this case, we have a is equal to 6, b is equal to 1, and c is equal to minus 1. Now, when we have a polynomial of order 2, which means that the biggest polynomial, or like the biggest power of x, is the number 2, we've got something called the quadratic formula. And the quadratic formula gives us the answers to our problems without really having to think about it too much. So if you've got a situation where it looks really gross because there's a non-prime number in front of the x squared, there's a mix of positive and negatives, or maybe there's really ugly numbers like 116 x squared where factorizing is going to be a real pain in the butt, what we do is we use the quadratic formula. And the quadratic formula is that the x, the actual answer to this whole shebang, is going to be given by negative b plus or minus b squared minus 4 times a times c divided by 2a, and then this whole term on the top is square rooted. This formula looks pretty gross, I'm not going to lie, when you first look at it. But when you're trying to factorize something that looks gross, this equation is actually going to save your butt. I don't want you guys to only rely on this, because knowing your multiplications tables and being good at factorizing means that you can actually solve polynomials faster than using this equation. But when you're stuck with a really ugly looking polynomial, when you're stuck with a really ugly power of 2 polynomial that you want to factorize, and you know it's going to take you a long time and you're stressed for time, this right here is a good fallback. All right, so we're going to have our b term was 1, but we have minus b, so that's going to be minus 1 plus or minus b squared, well, that's just going to be 1 squared minus 4 times a is 6, so that's 6, c is minus 1. All right, and then we're going to divide the whole thing by 2 times a, and a in this case is 6. Now notice that I've been referencing a, b, and c this whole time. Before you are super used to working with this formula, I highly recommend you really quickly write down what a, b, and c are for yourselves. Really quickly, because it'll help plugging in the numbers a lot faster. So negative 1 is just negative 1, plus or minus. Now this is negative 4 times 6 times negative 1. So the negative and the negatives are going to cancel. So it's going to be 4 times 6, which is 24. And then we've got the 1 squared, which is just 1. And then we're going to have x is equal to negative 1 plus or minus the square root of 24 plus 1. That's just the square root of 25 divided by 12. And here we see once again that being good at your multiplications tables makes the work a lot easier. We're going to have x is equal to negative 1. Now what times what gives you 25? Well, that's 5. Plus or minus 5 divided by 12. And then you see how we've got this little plus or minus? That's telling us that we've got 2 solutions. So we're going to have to pick both. So we're going to go with the positive one first. We're going to have x is equal to negative 1 plus 5 divided by 12. So we've got minus 1 plus the 5. So we're going to have 4 out of 12. And again, with the multiplications tables, that's just 1 out of 3. Now the other option is going to be the bottom one. So we're going to have x is equal to minus 1, and then it's going to be minus 5 divided by 12. That's going to be minus 6 divided by 12, and that's going to be minus 1/2. And then if you compare these two answers with the answer before, you'll see that we actually get the exact answer that we wanted. All right, so next is going to be our favorite part of the video, everyone's favorite part of the video, the fun bonus problems. All right, welcome to the extra fun bonus problems, everyone's favorite part of the video. So for the first 2 parts, we've got expanding and factoring. So for these 2, I'm really just interested in how you guys can make the expressions easier to work with. I'm not looking for a solving. I'm just looking for how do you get the x minus 1 times the x minus 2 to look like a big polynomial that looks like ax squared plus bx plus c. For the factoring problem, again, I'm not looking for the actual solution to x. I just want to make sure that you guys can actually make this x squared plus 6x plus 8 look like, x plus some number times x plus some other number. And then finally, for the solving problems, here I do want you guys to find a number for x. What does x have to equal to make these expressions true? And for these bottom ones, there's going to be a mix of different techniques that you're going to have to use to solve the problem. So give yourselves a second, and then I'll pop the answers up on the screen for you. So as always, the answers are in purple. Expanding and factoring are two sides of the same coin, the same way that multiplications undo divisions and vice versa. Factoring undoes expanding, expanding undoes factoring. And I'm saying all this so that A, you guys get it, and B, you can check your answers. You should be able to factorize from purple to black and expand from black to purple and get the same thing. Factoring, same thing. You can expand the purple to get to black, and you can factor the black to get to purple, so you can check your answers really quickly. One little note though about this guy right here. You see how it's got these really ugly terms in there? That's because, hint hint, we have a formula that gives us stuff that looks like this. But the quadratic formula gives you the answers. I'm not looking for the answers, I'm looking for the factor. Looking for the factor, not the answer. So just in case there's any confusion as to why this looks a little bit different. And then finally, for the solving of the problems, I won't tell you guys which techniques to use. You've been given all the tools that you need, but once you combine all the tools that you've been given, these are the actual values for x that you'll get. And if you're feeling a little unsure, remember, you can always plug your answer back into the original formula and you should get what the actual formula says you should get. So remember, it's always easy to check your answers, plug in x, make sure that when you plug in the value of x, your equation gives you something that makes sense. Now, that's everything for us today. I hope that you guys are a little bit more comfortable with expanding, factoring, and just dealing with polynomials in general. Hope you guys have a good rest of your day.